Okay, so good afternoon, everybody, and welcome to our colloquia. Today, our guest is Tom Richtler. You already seen him these days. He joined the observatory last Tuesday. It is really a great pleasure to have Tom here. It's been good these days to talk and work with him. A brief introduction, extremely brief introduction, I must say. Tom got his PhD in 1985 at the Bonn University, and then he got his habilitation, which is the equivalent of the Italian ASN, in 1991. And since 1999, he is professor at Concepcion Concepcion University in Chile. His scientific interests, it looks like your interest is everything beyond the solar system, but
I should start with the solar system.
That's what I was thinking about. Maybe he will start. So his scientific interests go from star clusters. Actually, I've seen that one of your first publications was on a color magnitude diagram of an opal cluster, which is stellar. So
I see that now.
So stellar photometry, which is one of the field, stars and how stars evolve, which was one of the great interests in the space. And so star clusters, early type galaxies, galaxy clusters, dark matter, cosmology. So there's a lot to fit in. And today, Tom is going to talk about modified Newtonian dynamics, a competitor to the dark matter paradigm. I'll give you 5 minutes ahead of time. Okay, so you're 45 minutes. Thank you.
Thank you very much, Mick. First of all, I would like to express my gratitude that I have the opportunity to speak at such a beautiful place. And full of shame, I have to admit that this is my first visit to Italy. But I'm also very grateful, Mick, that you helped me to wash out that dark spot on my CV. Yeah. I would also like to use the opportunity to make a bit propaganda for Chile as an astronomy country, especially for the younger generation. It might be very interesting during the last years to work in Chile with a privileged access to large telescopes to come. Also, the Cherenkov telescope array is in progress. The southern part is in progress, and as I know, we are the Chilean astronomers, have full access to the Vera Rubin database when it becomes operative. So this is all very nice. I have been urged, friendly but firmly, not to get lost in technical details. So I start fundamentally. So what is this? The product of the velocity of light. If you look at this, it's a dimension on acceleration. So sort of gravity. If Stephen Hawking would have been here, but he would say, that's all clear, read my papers, please. That's all. That was the beginning of a thermodynamical understanding of gravity, with event horizons of black holes have a temperature. Bekenstein, the great gravity physicist, then calculated entropy for the event horizon of black holes, and Unruh, I never know whether it's Unruh or Umruh in German, Umruh, generalized the Hawking radiation to whatever horizon, and with an acceleration, an accelerated observer sees in space-time which is heated up. And if you can heat up something, there must be a microstructure. That's the old Boltzmann argument. And so that was the beginning of the idea that there will be space-time atoms. And Gibbon and Hawking, cosmological event horizons, not only event horizons of black hole, but cosmological event horizons have temperature and gravity. And that was a seminal paper when first time the Einstein equation was written as a thermodynamic equation of state. And if you are interested in that paper, is quite recent. There is a good good summary of what has been done by now and how one can understand gravity as something thermodynamical. So this is the surface gravity of the event horizon of a de Sitter universe. A de Sitter universe is without mass, but with a cosmological constant, and it expands so fast that there's an event horizon. All clear? The content of my talk. I would like to do a few remarks on dark matter in cosmology. Very brief. What MOND, the beginnings, that was in the 80s. And the baryonic Tully-Fisher relation is the central relation of this talk. It's also possible to display MOND effects with other means, but this is the most simple ones. For spiral galaxies, it's more interesting than, well, I cannot say that more interesting, but it's easier to measure directly velocity in spiral galaxies than velocities in early type galaxies, where you normally measure moments, higher moments of the velocity dispersion. So, and this is more or less my field, but in the MOND regime, we have more difficulties to test MOND than the people who work with spiral galaxies. In the last year, gravitational lensing has become very important. I myself have never calculated a lensing map. This is weak lensing because strong lensing is not interesting. Strong lensing is done not by dark matter, but by normal baryonic matter. And but there are a few very interesting things, and of course, one would like to know what it's all about. So, to a general understanding of MOND within, let's say, the understanding of gravity, and this is not possible until now. It's not possible. That does not mean that there are not many theorists with many theories. We will see. Well, one count about 30 or so, and it always has to do, not always, mostly has to do with an extension of general relativity. Okay, a few words. The standard cosmology. The standard is, we have the standard model of elementary particles, and it's also unfortunate wording. I mean, the standard model of elementary particles describes very deep symmetries of nature. The standard cosmology probably will not persist for long, probably. How does these numbers come about? You have seen that probably many times, that 75% is dark energy and whatever, dark matter. How do we get these numbers? These numbers we get by putting many objects with known distances, supernovae, and also an object with also known distance, into the Friedmann equation, which are the Hubble parameter, Hubble constant, and the density parameters for matter, curvature, and cosmological constant. And then you get this out. And for a flat universe, you get very easily 1 equals this one. So dark matter and cosmological constant, dark energy, are not independent here. They are strongly coupled. And it is quite useful, I think, to think. No, I wanted to say something else before. If we calculate the second derivation here, because here is the first derivation, the second derivation, then we see very easily that it is very difficult to get it negative. It's always positive. So it's an accelerated universe. So we can go to the Nobel Committee and ask for a Nobel Prize. So they would say us, no, it has already been given for 10, 14 years ago. And well, I said I would not criticize a Nobel Committee, but I would encourage you to do the exercise. Go to the paper of Yoshi and Peterson. I do not write these names. Yoshi and Peterson, 1995. They're counting galaxies, and ask yourself, why these guys have not got the Nobel Prize, but the supernova guys do that. And if you find a good answer, tell me. Yeah. Dark matter here in that cosmological context is to a certain degree, is self-contradictory. We need the homogeneity of the Friedmann equation to get these numbers, but simultaneously we need dark matter to form structure. That means to violate the Friedmann equation. So most people ignore this problem, but a few people do not, and they say, yeah, the university approximately is a mystery, and the possible part of the solution that the dark energy is an artifact of describing an inhomogeneous university by Friedmann. That is the point. And if you are interested in that, the key word is back reaction. Back reaction. You find a lot of literature on back reaction. This is Thomas Buchert, and this is a nice description of what is going on if we look at a non-homogeneous universe. So that's and cosmological particle dark matter does not exist either because, yeah, well, we do not know, but there is until no evidence for its existence, not at all. And in spite of that, more than 500 pages on dark matter. So that means that scientific truth is not always trigger for scientific activity, but something different. I must say that I can say that in the next point. In Chile, there is also a small group of astroparticle people, and I'm following their seminars and so and I recently heard seminars on the dark photons and axions and all that, and I'm always amazed that how much fantasy, how much power, how much physical charisma they invest in populating the universe with particles that do not exist, that very probably do not exist. The standard model does not know such particles. And the standard model has an immense predictive power, immense predictive power. Although they have a few Nobel Prizes. They have not been found in spite of very ambitious searches. I mention only this high altitude water Cherenkov telescope because I myself am on the CTA consortium. I wanted to be close to if they detect gamma rays from hypothetical decay products, I would like to experience that as well. But we'll see. The probability is not very high that they do. They must explain the extremely close relation of baryonic dark matter that we'll see what that looks like. And there is another point which normally they do not spell out. They must generate gravity. That would be a new phenomenon. Our gravity here, our macroscopic gravity can be traced back to the proton mass. And the proton mass has nothing to do with the rest masses of elementary particles. It is the some hadronic chaotic energy divided by c squared. But no, yeah. So, but that may be a good assumption. And the main protagonist, I do not want to go through all things, but I just want to let you know that if you like to look into the literature, please ask me, and I give you the slide or the whole paper, the whole talk. Yeah, the MOND white paper is now in progress. It's ready, and Lelli, Federico Lelli is the main author, the prime author, and he was also the initiative behind all that. And it should come out very soon. And he wanted to have it not like a review article, but well, like a vision more or less. But the theorists in all that group, they made a good review of their theory that is 1/3 of all the things and difficult to understand sometimes. Yeah. I said starting with the solar system. This is a rotation curve, and historically, the 1 over R2 force comes from that curve. Until here, that's for the time of Isaac Newton and Robert Hooke and all that. And we have the circular velocity. We also use the term circular velocity also in the case if there are no circular orbits directly visible for elliptical galaxies. So this is this expression. Here there is no mass discrepancy, so there is no dark matter in the solar system. These asteroids or whatever, or comets do not count much. We go to the beginnings of Rubin Ford. The rotation curve of the Andromeda Nebula was the first. They got out to 24 kiloparsecs, but here it's still not really visible that it's becoming flat, that larger. This is better visible if we look at, this is also Rubin 78, at other high luminosity spiral galaxies. They go out to also 50 kiloparsecs, and we see that for NGC 801, it becomes quite flat. So this is from the original paper. And in 83, this is a citation from the Faber and Gallagher review on dark matter, and they say that the case for invisible mass in the universe is very strong and getting stronger. And Moti Milgrom made another proposal, let's say, because there was nothing known about galaxy dynamics at this time, hardly anything. They made another proposal as a possible alternative to the hidden mass. We'll show how that works. The MOND pages by Stacey McGaw are very well maintained, and I can only recommend to look into the MOND pages. I show here the citation record of Milgrom's paper, and you see that until 2000 or so, well, there was not much notice of the work of Milgrom, but now it's going up, and I think it has the full potential to be one of the most cited papers in modern astrophysics in a few years. The idea is only the basics. The recipe for an asymptotically flat rotation curve, that is the point. He wants to have flat rotation curves without dark matter. So by gravity, that means we have to have a 1 over r law instead of a 1 over r square law. That means that this square root takes care of this, but then we need to multiply that with a constant to get the acceleration dimensions right. So we have this for the asymptotically flat rotation curve in the case of very, very low accelerations. And already in the first paper, Milgrom noted that it was something, the A0 was something like c times the Hubble constant. We are now at we know more, and at this time I do not think that Milgrom was thinking of the de Sitter universe. Then for circular velocities in the asymptotically flat rotation curve, the mass depends of the radius becomes constant because there is no galaxy anymore, and then there is a constant, and we need to have all galaxies to follow the baryonic Tully-Fisher relation, and this is one of the central tests of MOND. Once again, Milgrom knew only the very top of the luminosity function of galaxies. He did not know how dwarf galaxies would behave also. So this is an extremely strong prediction of MOND that these must be fulfilled in everywhere. I do not want to go into the details here, into the technical details, but it has quickly shown that simply replace the Newtonian law by Milgrom's recipe does not work for energy conservation and all that. So they needed a Lagrangian. I do not go into the details. The paper is here. And if we have configurations of high symmetry, so elliptical galaxy, we are content with this relation, where this is the MOND acceleration, the Newtonian acceleration, and this mu function in dependence of Gn divided by A0 is here an arbitrary function which interpolates between the Newtonian regime and the MONDian regime. And for most, for our purposes in elliptical galaxies, this is okay. It can be, for example, x over x plus 1 would serve it. What's the purpose? How to test MOND? Galaxies with disks, we can measure rotation curves. Galaxies with, without disks, virial theorem, and bright galaxies and clusters. I do not want to talk much about this because galaxy clusters are very not good objects for MOND testing. In the last years, gravitational lenses will become more important, and we'll see a few things. This was one of the breakthrough, I would say, by Stacy McGaw. He was showing the flat rotation curve for spiral galaxies versus the stellar mass. Here's the stellar mass from 10 to the 6 to 10 to the 11 solar masses, and you can see that for the lower mass, so it's a dwarf regime, that does not work. But it does work if here the say the baryonic mass is indicated as the sum of stellar mass and gas. If we move that here by looking also at the gas content, because here this dwarf galaxies are quite gas rich, and sometimes it's the gas mass is as much as the stellar mass. We have as very easy to remember relation 50 times the flat rotation curve to the fourth power, and this must be realized everywhere. This is one from Lely's Spade later work where he or they insisted on the high data quality, and so they got 3.9 instead of 4, but I think this is a good confirmation. This is the gas fraction, and you can see that for the blue dwarf galaxies, that's almost half of that is next. Our profession was to investigate elliptical galaxies, and I like always this M87 because there are so many globular clusters around, and we need to assume a spherical symmetry, which is not always maybe given, and then we measure the projective velocity. I mean, you have done that yourself probably. I can be very quick here, but I have made the experience that this was a point which was not well understandable by students, because if I got that question, our students see that and they say, they do not realize that an elliptical galaxy is transparent. It is like glass. So if you look through it, you get contributions at every point along the line of sight. That should be said. Dynamical tracers, that we do not need, I think. Also the genes models we do not need. I think you are well, you know that all. Genes Jeans models are not, to apply Jeans models is not the only way to get masses for elliptical galaxies, but one should remark here that an ideal Jeans world is spherically symmetric. So that means that the radial coordinate is the only variable along the event. And if this is not realized, the line of sight, then we have. That was our galaxy sample, which over the years I showed to Mick yesterday. This example, there is no dark matter visible, and it's a bright galaxy and very good data. And I don't know what happened. It's possible that it's not spherically symmetric, and that there's a disk, a contribution along the line of sight, which lowers the velocity dispersion, the projected velocity dispersion at larger radii. Here we worked, Ilva Schubert, that was the PhD thesis of Ilva Schubert, and we worked years on that until we got more than 400 radial velocities with force. No? So that was a lot of work. Then we have the central galaxies, and this is a well-known galaxy also here in the Hydra cluster, and there come other problems. The measurement, spherical symmetry, rotation, this is all not always given. Sometimes it is given, sometimes it is not given. And this is an example for 636. This is an extraordinary galaxy. It's quite bright at the outskirts of the Vega cluster. And has more than 6,000 globular clusters. So we had a lot to do, and that is our MOND model when we at the end, and it looks more or less what we can expect. Here, that I would like to take more of this. I did not do a review on early type galaxies, but in this paper I tried to summarize what was known a few years ago. And probably you know the SLUX survey of globular cluster velocities. No? This is maybe until now the greatest survey of globular cluster velocities in elliptical galaxies, in, I don't know, 30 or so elliptical galaxies, 25, with a few thousand velocities. And here I plotted a few different samples. The decent sample at all of early type galaxies is one of the best one regarding the data quality, and I think that reproduces quite well the locus here for the spiral galaxies. No? This is not a fit, but it is the locus of McGaugh's spiral galaxy baryonic Tully-Fisher relation. If we I don't know whether I do a mistake, but if I took the masses of the SLUX survey, so it is very clear that many galaxies do not fall on the baryonic Tully-Fisher relation for the spiral galaxy. Why? I think one has to look into every galaxy, and the data quality is a very strong parameter. A few of them galaxies have just a few velocities, 8 or 10 or 15, and so of course you cannot derive a reliable mass from this. These strong deviators, these are all galaxies in the centers of galaxy clusters, and they are very different from the others. This I like, because we have 10 to the 15 solar masses until 10 to the 8 solar masses here. These are galaxy clusters from X-ray sample from La Ocre. This is the old decent sample which we have seen, and this is a dwarf sample of Kurapati et al. With the particular properties that these are gas-rich dwarf galaxies in a void. So in a void, which also in the lambda CDM world should not contain dark matter. In spite of that, again, this is not a fit. No? They rely on the same, almost exactly on the same relation as the spiral galaxy. Galaxy clusters, this cluster is a mess, and I talked yesterday to Mick about it, whether I should say more about that. Probably not. I do not. If you ask me, then please after that. I claim that this galaxy here, that is an isolated elliptical galaxy, does not look like that, no? I claim it is an isolated elliptical galaxy. The reason is that we see here a projection of at least four groups of galaxies. I prepared a velocity histogram, which I do not show. How much time is left?
15 minutes.
Yeah. This is just for the beauty of the many globular clusters. That's 1399, and we worked really hard. Or Ilva also worked really hard on that. But we did that together more or less, and to get mass profiles for 1399. But this is even more interesting. 133311 in the Hydra cluster that was still with the Force 2 instrument, and you see a few long slits and here the slits of where we took spectra, and we can put see a rising velocity profile as we see also in other central galaxies. And my point here in the thing is that it's not an ideal Jeans world. No? Ideal Jeans world must have at one radius, one velocity dispersion, but not a range of velocity dispersion, one velocity dispersion. And how this comes about? Probably because there are so many traces with so many different properties, and different traces are characterized by different potentials, which they have to traverse, and so on and so on and so on. This is a complex situation and not really suited to test MOND. Here I wanted to show that even for MOND models here, so these are MOND models, so no dark matter and nothing. And here are different density distributions with different core radii. Here the core radii plays a big role, because with a high core radii you have more objects which have larger potential differences, than with small core radii, which are always in the center, and do not see the potential differences like the larger core radii. So these models here, also bit radial, show that even in the MOND conditions, we get velocity dispersions like 800 or so. So we cannot derive serious mass from that. It's not possible, I guess. Now, the gravitational lenses, which it's not my own work, of course. And here it's just for its beauty, the almost complete Einstein ring. But this is strong lensing, and strong lensing has nothing to do with dark matter. The gravitational fields are much too high to be in competition with the MOND region. So they are not MONDian. What we need, or what people need, is weak lensing. And the weak lensing, as you know, probably the statistically deformed images of background galaxies, and we need for that, we need isolated galaxies on a background of many redshifts. This is the point, because we need for each image, we need a redshift, and the very pioneering work on that was here from the Groningen people, of Bauer et al. But I do not want to discuss this more because it does not show a baryonic to the Fisher relation. It shows different things. But the follow-up work by Tobias Mistele et al. Shows more or less the same. They confirmed that more or less. They have flat circular velocities out to megaparsec scale. That is the point. That was Mistele 2024 for late type galaxies and early type galaxies, and here they the baryonic to Fisher relation, and this goes out to 1 megaparsec. Here one example, one explicit example is that from these galaxies, which they show, and they show a weak gravitational lensing signal out to 800 kiloparsecs. What do you think? You can think, I do not believe that. It's all. Huh? Or you think there's no dark matter? I do not think that there is a third possibility. Yeah. Yeah. I do not want to say much about the theories, but to give you an impression what is going on. Huh? Here, these are, I think, 28 different theories, and here are the references, so you can work your way through all the references if you during the next 30, 40 years. But there is one deviating, well, this is all modified gravity theories, this one, and Milgrom always did not like that. So he thinks that MOND is essentially a modified inertia. You cannot distinguish between whether you modify this or you modify the force here. And apparently, nobody followed him because it is, I think, that is my impression. For theorists, it's more interesting to extend general relativity, because this is what it's all about. You need a general formulation of MOND, a general relativistic formulation of MOND, which you already, that I forgot to say, which you already need for weak lensing. If you to calculate photon paths, this is not Newtonian, of course. So you have to choose one of these many theories, and I think that is the situation nowadays. So me as a simple-minded observational astronomer, I cannot comment much on that, I must say. I'm also not sure whether this impresses me so much. Yeah, I don't know. Milgrom himself, that's good. I was present when in one of the MOND papers when Milgrom commented on one of the theories and said, "Yeah, this is the gravitational theory of the poor man's gravitational theory." So it's not over the discussion, and I think I do not want to. Let's go. I wanted to show how Milgrom does it, because this is more easily understandable. But I suggest that you take these slides and read by yourself, because this is yeah. So this is what comes out with modified inertia, and so this was I forgot it. That's what I wanted to show. The Milky Way rotation curve from McGaw, and these are the Gaia data, and this is McGaw's MONDian model. So it's not a fit. He insisted that it's not a fit to the data. That was a prediction of the MOND model. and apparently a good prediction. Was that? Yeah, this is now the baryonic Tully-Fisher relation as it appears in the MOND white paper, and that goes over 9 orders of magnitude. And Lely himself is in thinks there is still dark matter in galaxy clusters. I do not think so, but yeah, we'll see. Okay, cosmology. If you invite Pavel Kropa, he will tell you more about cosmology. I cannot do that. But there is an old paper by Bob Sanders from 98, where he already calculated or estimated how MOND forces stop the Hubble expansion very early, and then form structure at very early times. The massive galaxy was formed at Z40, and at Z15, they should be already virialized in this scheme. That's what we see now. Huh? That's from 98. And that is what I found as a candidate, let's say, for the most distant galaxy at Z equal 30, the Kaputaurus. Do you know that? I didn't know that. I was just Googling for the oldest and most distant galaxy. So, but it's a candidate. It's not, well, they say that there are strong arguments for Z equal 30. But this is expected with MOND, with MONDian structure formation, very early time, and that you should take away. Yeah.
Thank you, Paul. And people attending remotely, if you have questions, unmute yourself and ask. And we have here our participants. There is thank you. There's a lot to digest. Enzo speaking. Please.
So, first of all, ciao, Tom.
Hi, Enzo. What to hear you, to see you?
Is here.
Yeah.
From here.
Thanks a lot for the seminar, first of all.
Hi, Enzo. Yeah.
Yeah, hi.
Long time ago, yeah.
Yeah. Both of us is very young, let's say. Okay. Very interesting seminar. Let me just ask you one thing, a curiosity. Do you think that the ELT will be a game changer in this matter? Do you expect new, very fine, very precise velocities from him to
I think,
weak?
I mean, that will be a science driver for the ELT. I think it's clear. But I wouldn't do any prediction whether. But yeah, probably yes. No? I think that's an obvious thing to do, to look for 30 Z equals 30 candidates. More and more and more. Yeah. Yeah, I think so. Yes. Yeah. But what? Yeah. I don't know when it will be ready. Maybe in 10 years. Less.
Yeah.
9.
It's moving fast.
Well, no, I'm 73, no? So that's 9 or 10 years make a difference.
Okay.
So you obviously thought a lot about that and studied a lot about this. And we were, most of us, educated in a system where that pattern is the standard paradigm. And MOND is just, folk event that people think then.
That where you remember the citation history, no? You are then in that sense on the
For that,
Yeah,
well,
no, that's
please do. Well, but no, I mean, and
so many
that's it.
many people are. Many people are.
No, I'm not saying no. I'm not saying that this is right and that's wrong. Just saying that we haven't thought about that enough. I mean, I've done a couple of quick introduction reviews, for your presentation, and there's a lot to digest here because this mainstream science is all about that matters, and that is the other thing. I understand that you probably make a point that MOND fixes a lot of stuff, and more than I understood, because I understood that it fixes a lot on galaxy scale, but it doesn't fix too much enough on two sides, on the cosmological scales, and maybe Pavel, as you said, it doesn't agree with that. But it's also it's more like a phenomenological interpret. It has some pieces of the puzzle that go together very nicely.
It's like the 1 over r square interpretation of the rotation curve of the solar system. That's also phenomenologically.
Yeah, but
That's not. It's not measured on Earth.
Newton principle.
Yeah.
Well,
How would you?
no. I'm not saying that. So what I understand is that there is more that there's a lot that is not explained by MOND, and that explained by other theories. So why do the
MOND now follows if it's the thing for a weak gravitational field covers almost the entire astrophysics.
Does it?
Yeah. And I mean, what in the white paper? I mean, there are a lot of things which I cannot touch and which I do not understand. No, but that's a very personal impression. I mean, there are prominent figures in in business, the dark matter business. So Simon White, one of the, Volker Springel is now one. There was a very good talk by Volker Springel that I heard, which was very illustrative for me, where I had the feeling they distracted their interest for dark matter. They are not longer interested in that. They're interested in other things, where they need computation power. With gravity is dissipationless. What you need you do not need a laptop for gravity. You do not need the computing power which they now have. That is what they need for dissipational processes, like star formation, supernova, and what. Like the climatologists. That is always my example. The climatologists are not interested in gravity. In spite of that, gravity is essential for them because it makes the air pressure. But why it makes the air pressure, they do not care. In a similar sense, that is not a bit. I have the feeling, and also I gave a talk at Bochum University where there are representatives of the lambda CDM model. Let's say there is Hendrik Hildebrand. And he himself is a co-author of that MOND paper, recleansing. Well, I think that's also one has to get accustomed to a certain sort of thinking. But dark matter has never been seen.
That's pretty clear. Yeah. So, which doesn't. It's a statement that by itself doesn't mean much. I mean, it hasn't been seen, doesn't mean. But it's been popular and very popular.
But it's becoming less and less popular.
Yeah, you're right, because there are a few different opportunities. One of them is now changing run, not dynamics.
Yeah.
So going to the most observational part of my interest, kind of catching up with Enzo's question. So there will be now in the future, this massive spectroscopic surveys of the entire sky. And I really hope that 6-8 meter survey telescope doing spectroscopy of all globular clusters in the local universe. So globular clusters go well beyond extragalactic globular clusters, go well beyond the stellar and gas detection for spirals, and beyond you can do globular clusters not only for spirals, you can do them for ellipticals. How well constrained is MOND there? Because I mean, globular clusters, you might not have this big chunk of data.
You mean on the scale of a globular cluster, or globular clusters as traces?
Oh yeah, that's another different. I'm not asking yet, but that's also interesting. No, I'm asking about how easy is to constrain MOND with something that's not specifically circular, like like stars and spirals, but then something which, like globular clusters, are their orbits. So is it?
Yeah, this is exactly that is our point, no? And we
works as well as so. And then this spectroscopic surveys will give us.
If you have, for example, I would say if you have 500 velocities, then you can do something with that. You can also identify anisotropies and all that, which you cannot do with 10 velocities.
Okay, so that will be
so. What if I would have time? I would have go back to this Lux survey, because there are still a few galaxies with 300 and more velocities which have not been looked for MONDian effects.
Oh.
But it's very easy. They're all published.
And then the question you asked yourself: what is MOND for globular clusters? I mean, dynamics.
Yeah.
There's something.
Yeah. Then it becomes a bit complex, because then you have to leave that that simple spherical symmetric approach, and the globular clusters of the galaxies are in the wider galactic field, gravitational field of the galaxy. So, but it may be that there is a MOND effect within galaxy. They call that the external external force, or no, external, I don't forget, MOND effect. And some people say, yeah, you can see, and other people say, no, you can see that. Or in white binaries, you also, there's a long discussion going on whether you see MOND effects in white binaries.
So you need better data. That's
yeah. But some people do not wait for better data, but work with what they have.
Right. Soon we have plenty.
Yeah.
It already changed maps.
Yeah.
I don't know if there are other questions. Otherwise, let's. There are questions from remote. Otherwise, let's thank Tom again. And ciao to everybody.
Grazie Tom, ciao.
Ciao.
Ciao. Next seminar is in a couple of weeks by Antonio Lamarca. We're going to talk about